Alrighty, so hello again. We're officially getting started with today's session. The format looks a little bit different to anyone who's watching later because we're using GoodNote today. I felt spicy. So we're going to start out, as always, very briefly reviewing what we did last time, which was some more reactions. So we talked about the enamine reaction, which is very similar to the imine, except now we are going to have a double bond between the two carbons and a single bond to the heteroatom. So that was a little bit funky. Now, after the enamine reaction, we're going to move forward today. I don't know why the page is a different size, but we're just going to roll with it. So we're going to start with that is much too thick. The hydrozone reaction. So the hydrozone reaction is going to, again, start out with a ketone or an aldehyde. And the reagent in this case is going to be, I want this to be pink. No, I'll just do red, it's fine. Okay, so we are going to use H2N and H2. And I like to use, oh my goodness, I like to use HCl just for consistency, but it could be done with an acid or a base. So, first thing is first, we're going to name this guy. This is our hydrazine, and that is going to be our nucleophile. All right, so I'm going to try, since we are so close to the exam, and I do have recordings of these like full mechanisms on the YouTube channel, I'm going to go through the fast mechanisms, and we're going to kind of do it more like a summary. If anyone is super against that, let me know, but I promise we will cover everything you need for the exam. All right, so first thing is first, we know that the acid catalyst makes the electrophile more electrophilic, so we end up protonating. And yes, I can repeat what I said. So I promise we will go through everything we need for the exam, but I am going to do these mechanisms kind of shortened so that we're going to do like the summary stuff. You don't have to know like the step-by-step pushing arrow mechanisms. You just have to know the main ideas. So for this one, the main ideas you have to know. It gets protonated, whatever. Why is this so difficult? I'm not liking it so far, guys. Okay, so gets protonated, and now the nucleophile is going to attack. So our nucleophile is the nitrogen. In this example, does it matter which nitrogen we use? No, because they're exactly the same. So, all right, the nitrogen is going to attack. These electrons are going to go up. And we end up with OH, N, NH2, H, H. So we know we're unhappy. And we know at this point from all the other mechanisms we've done, we know that oxygen is going to steal a hydrogen. And this is where I'm shortening it. So if you get lost, let me know. And then we know that nitrogen uses that lone pair to reform a double bond. And it kicks off the the water group. So this looks like so now. Are we sort of kind of okay with this? It's a whole cycle of arrow mechanisms, yes. Usually I would have done this in 3 steps, but we're just doing the Rosemary method now. We're just trying to boom, 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 go through it. So once we have this, we have that pesky plus charge, and everyone please remind me, what's the easiest way to get rid of a plus charge? Deprotonation, exactly. So we go bam, bam, and we end up with bam, bam, double bam, bam. And this fella is called the hydrozone. No, it's hydrozone. Okay. So the main idea is ketone or aldehyde plus hydrazine equals hydrozone. But wait, Rosemary, how will we ever remember which one is a hydrazine and which one is the hydrozone? I'm so glad you asked, friend. Okay, so this is really dumb, but stay with me. So the hydrazine goes into the reaction. Hydrazine, it goes in. The hydrozone goes out of the reaction. Or, if you want a better way to remember it, the hydrazine goes in, and then, oh snap, we're done with the reaction, we have a product. Hydrazine is in, hydrazone, snap, we're done. That's how I prefer to remember it, but whatever butters your biscuit. I'm sorry, I can't believe I said that. I'm so tired. Alrighty. I appreciate that you guys have started saying LOL in the chat as to make me not feel awkward. It's much appreciated. Okay. So yeah, that's pretty much it for this reaction. It's a genuine LOL. I'm so glad. Okay. So the next one is very similar. We're going to call it the phenylhydrazone. Oh, okay. Reaction. And the phenylhydrazone is pretty much exactly just like the hydrazone reaction. So we have a ketone or an aldehyde. We're going to draw a long arrow because this reagent is big AF. So we have H2N, NH. Wow, hydrazone. And then all we attach is a pH for phenyl. So I'm going to write pH equals this guy. And just like every other one we've done, we're going to have an acid or a base, and I like the acid better. So, step number 1, the acid catalyst makes the electrophile more electrophilic. So we get the same thing we do every single time. Ta-da! And now we have the nucleophile attack. So we're going to find out which of these nitrogens will be the nucleophile. So we can say nitrogen A or nitrogen B. What do we think? Which one will act like a nucleophile? We got one person that says A. A, cool. Yes, I totally agree. So I want you guys to keep this in mind. This nitrogen in the middle is much too sterically hindered. There's too much stuff going on. It cannot be the nucleophile. This one has to be. So we're gonna boom bow attack. And we get this ugly monstrosity. Literally, look at this. Disgusting, right? And just like we've done in every other reaction, we're going to have that lovely intramolecular proton transfer. We're going to give those electrons back. Nitrogen is immediately going to use those electrons to reform the double bond and kick out the leaving group. So we get nitrogen with a hydrogen attached to another nitrogen with a hydrogen attached to a phenyl. And wow, we have a plus charge. Whatever will we do? We're going to deprotonate with our handy dandy Cl-. Bam. And we have got ourselves, ladies and gentlemen, a lovely phenylhydrazone. Okay, cool. And can anyone guess what the nucleophile was called here? So what's the name of this lad? Phenylhydrazine, exactly. They are not creative here, folks. Oh, what have I done? Bam pow. So once again, the phenylhydrazine goes into the reaction. We do a whole bunch of steps, and pow, we get a phenylhydrazone out of the reaction. And again, this could happen in acid or base catalyst, makes no difference. Any questions, comments, or concerns? Yes, I can definitely zoom out so you can see both. Okay, so we're good with this one. Let's go on to the next one that's kind of similar, but a little bit more straightforward. We're going to call it the oxime reaction.
Oh, you are pretty okay. Go ahead. I'm done. You ready?
Now, what the heck is an oxime, right?
Let me see. I want to put on the computer at home. Yeah.
Thanks, okay. So the oxime reaction, just like all the other ones we've done, starts with a ketone or an aldehyde. And now we're going to have that spicy NH2 again. The only difference is we replace the other nitrogen with an OH. Gasp. This is not going to be a wildly different reaction. We're still going to have HCl. And as always, the first step, we just steal that hydrogen. right? We know that by now. So, plus. Now, the question here is, which one of these lone pairs is going to act like a nucleophile? Is it going to be nitrogen or is it going to be oxygen? What do y'all think? Who's going to be our nucleophile? And remember, if you get it wrong, nothing bad is going to happen. Ooh, I'm so happy to see the answers. Okay, so some people said nitrogen, but a majority of people said oxygen. So let's talk about that real quick. So we have nitrogen and we have oxygen. Remember, sorry, I just got distracted. Remember earlier in the semester when we were talking about acidity and basicity trends? Which one of these guys is more acidic? Oxygen. And is it more or less electronegative than nitrogen? More. So since this one is less electronegative, it's going to be more basic, right? So with this in mind, which one of these two atoms is going to be more likely to donate its electrons? Everyone's like, I'm changing my answer, nitrogen. Yes, exactly. So remember, nitrogen is more likely to donate electrons to act as a base or as a nucleophile. So this is an important concept. It's important for you to know the idea behind it. So if I ever ask you which one is going to be a nucleophile, nitrogen or oxygen, the answer is probably going to be nitrogen. So if we take that logic up here, the nitrogen is always going to be the one to attack. So we're always going to add the nitrogen to the carbon. And we get OH, and we get NH2OH. So at this point, we do a handy-dandy intramolecular proton transfer. Oh, that actually looks mighty ugly, so I'm going to fix it. There we go. So we steal one of the hydrogens, give those electrons back. Then nitrogen is going to form a double bond, kick off our leaving group, and we get, and I see that there's a question. Let me just finish drawing this and I will answer it. And while I'm answering that question, I want y'all to tell me, how do we get rid of this plus charge? And yes, I can definitely scroll so you can take a picture. And someone asked, if we have two possible nucleophiles within a molecule, we choose the one that's more basic. So yes and no. I don't necessarily want you to think basic equals nucleophilic. It is the same trend, but I want you to think more, which one is more likely to donate electrons, right? And if we know that nitrogen is more basic than oxygen, we know that it's more likely to donate its electrons. So your idea is right, but I wouldn't necessarily use those words so you don't get confused. if that makes sense. Okay, cool. So, as you all know by now, we're going to use our buddy Cl-, and it's going to sneak in over here and steal the proton, and we get, boom, bow. Does anyone want to guess what this product is called? The oxime. Absolutely genius. And, okay, cool. I thought it just wasn't going to write anymore. I was like, that would be unfortunate. So here. And to the person who sent me the comment about the pen sizes, I am going to copy that into my notes. Okay, cool. Thank you for the tip. I appreciate it. Okay, so any questions about the oxime reaction? How do we feel about it? Don't reopen. Thank you. Oh, you're so right. So the nucleophile here is just called a hydroxyl amine or a hydroxylamine. And we have a hydroxyl and we have an amine. So let me zoom back out. So, okay, I can draw it out here too, just so you can see it. So a hydroxyl amine is anything that looks like HO, the hydroxyl attached to an amine. And that's going to be the nucleophile in this reaction. Ta-da! But the point is they block. Make more sense? So I can only. I hope so. So I have to get them unblocked. So okay, how? Okay. Why they block? Okay, so I don't see any questions yet. Okay, if that's the case, we're about to do my most favorite reaction of the whole entire semester. I truly cannot wait to show it to you. So I will give you one more second. If anyone needs me to go anywhere to take a screenshot or anything, let me know. If not, I am pumped. Okay, spectacular. So we're gonna do something called the Wittig reaction. Bum, bum. And Dr. West has a fancy accent, so he says it more fun than I do, but the Wittig reaction. Yay! Okay, so the first part of the Wittig reaction is actually making the Wittig reagent, and we call that the ylid. So, step one, making the... Nope. I think that's how you spell it. That's absolutely not how you spell it. No, it's okay. Okay, sorry about that. So, We're making the illid, which is definitely not spelled like that, and I will look it up after the session. But so we're going to start. Oh, thank you so much. I was almost close. Thank you so much. Okay, so
I got a green band. All right.
we start with
Where's the roll down thing that you was telling me about? Okay.
something like this,
How did you go on there?
aka an alkyl halide.
I wouldn't watch.
And we're going to react the alkyl halide with a very specific reagent. And we're going to even pop out a different color for it because it's so fun. We're going to call it PH3. And that's called a triphenylphosphine. Try saying that 3 times fast. And in the first step, we are essentially just taking this and replacing it with this. So we get, bam, bam, bam. But now we have an issue because the phosphorus has a plus charge, and the way we're going to get rid of that plus charge is by reacting with a strong base. Excuse me, I have the hiccups. And the strong base we're going to use here is this guy. And I'm showing it to you visually because I like visuals, but I will also write it out for you. So this is C6H5Li. And essentially what that base is going to do is it's going to steal that hydrogen and give those electrons to that carbon. So we end up with a plus. And we get a handy dandy little minus here. Also, I am so sorry. There was just so much noise that I could not focus on anything. So I apologize for completely like spacing out for a second. I hope that wasn't too distracting. Okay, so at this point, yay, we have made our illid. Woohoo! What I want you to note is that this guy kind of sucks, right? He has a plus sign and a minus sign. We don't like that. So we can do some handy dandy resonance. And we can bring this lone pair here. And we can get this. Right? And since these are a pair of resonance structures, both of these structures are called the illid. And I spelled it wrong again. Jeez. I'm not an English major for a reason. So if he were to theoretically, wink, wink, nudge, nudge, ask you which of these is the illid, both of them are the illid. They are 2 different resonance structures. So any questions about making the illid? And I will also note that the illid is the Wittig reagent. Okay, so I can definitely scroll up, unless you want to see both of them at the same time. So we're not done with the Wittig reaction. All we've done is for freak's sake. all we've done is made the Wittig reagent. So I'm going to give you guys a moment, and then we're actually going to do the Wittig reaction. Okay. Sorry, I don't know if you were done. Let me know if you would like me to scroll again. I'm so sorry. You were done? Okay, cool. So the actual Wittig reaction is the fun part. So the Wittig reaction is going to start with, you guessed it, a ketone or an aldehyde. And instead of filling these things in, for now I'm just going to say let's call it R1 and let's call it R2. The important thing is that we have a carbonyl, right? And we react with our eraser, apparently. Nope. We react with our ylide. So the actual Wittig reaction is between a carbonyl and the ylide. So I'm going to show you two ways to do this. First, I'm going to show you the scientific way, right? And then I'm going to show you the Rosemary method. So as we know, the ylide looks like this, but it also, this is terrifying, it also looks like this, right? So that negatively charged carbon acts like a nucleophile, and it's gonna, boom, attack this carbon. This carbon doesn't like that, so now it's going to use these electrons to push up to the oxygen, and the oxygen is going to attack the phosphorus. There's so much happening, right? So we're going to draw the box intermediate. And so the oxygen has one bond, and it's attached to R1 and R2. And now this carbonyl carbon is attached to the carbon of our ylide. And for all intents and purposes, I'm going to call this R3 and R4. Right? So R3 and R4 are just hanging out. And they're still attached to the phosphorus, which is attached to pH, pH, pH. And last but not least, the oxygen and the phosphorus have a bond. Does this thing look happy? No, I would agree. It does not look happy. It looks disgusting. So let's fix it, right? Something you might not know is oxygen and phosphorus have a very high affinity for one another, aka they're madly in love, right? This is going to sound so stupid, and I know it is, but just go with it. So the oxygen and phosphorus want to be together forever, right? So oxygen is going to use its electrons to, how? Double bond that. So once it's double bonded, it's really committed, and the phosphorus can finally let go of carbon. So phosphorus ditches carbon and gives those electrons back. Carbon doesn't want to be alone forever, so he gives his electrons to the other carbon, and they make a double bond. And now that they're happy, the carbonyl carbon can finally let go of oxygen, and it gives those electrons back. Basically, we've just gone through 3 seasons of a soap opera and 1 reaction mechanism. And now we get R1 and R2 is double bonded to R3 and R4. And our side product is oxygen double bonded to pH3. So these are our 2 products. Gross. I know. I know. So this isn't too hot. We don't love it too much. But we are going to give it the rosemary touch. So I will give you a moment while I add a new page. And I will give you a second to screenshot, whatever, ask any questions you would like. Okay. So let's do the rosemary mechanism. Like in that elevator I have. Okay. So the rosemary method is a lot more straightforward and a lot more fun. And it's going to sound really weird, but trust me, it will stick in your brain forever. So, Halloween is the best holiday. No questions asked, not up for discussion. And so, since it's the best holiday, we're going to pretend it's Halloween right now. And we're going to be Frankenstein for a second. And Frankenstein, since nobody can argue with me, was an absolute freak of nature, right? And so we are going to be absolute freaks of nature. So, what I'm going to do, and stick with me, trust me, there's a method. We're going to treat these like little creatures, right? Because we want to create a brand new creature. So we're going to cut the head off of this molecule, and we're going to cut the head off of this molecule, right? And because we're actually insane, oh wait, I'm a dodo head. I got so excited. Sorry, I got too into it. Okay, so we're gonna cut the two heads off, right? And what better to do than to connect the two heads, right? So we're gonna attach the oxygen to the phosphorus. Let me zoom out a tad. And now you have one freaky little two-headed monster, right? And now you have a whole bunch of limbs, but you don't have any heads. So your second monster is going to look a little bit funky. We're basically going to take the arms of this monster and the legs of this monster, and we're going to put them together. So we take the arms, we give it a trunk, which is its body, and instead of a head, it just has two lovely legs. So let's write the very professional scientific notes. Cut off the heads. Stick arms and legs together. Ta-da. Sounds kind of gruesome. That's the whole point, Melanie. Now you'll never forget it. You might be wondering if I'm okay. That's besides the point. I'm kidding. Okay, so how do we feel about the rosemary method? 5, easy. Sweet. Okay, so I do have a little demonstration to show you, and there's a lot of people around, so it's going to make me look like a freak, but let's do it. Yeesh. Okay, so this reaction is like super, super specific, right? So R1 and R2 have to be on the same carbon. R3 and R4 have to be on the same carbon. You can flip-flop the two, but you can't switch across. And so my demonstration is R1 and R2 are my arms. R3 and R4 are the legs, right? So I can connect my arms like this, or I can connect them like this, And I can connect my legs like this, or I can connect them like this. But I can't take my hand and trade it for my foot, right? So I can't like crisscross, do all that kind of stuff. But I can attach my arms this way and my legs this way, right? So that translates to we can have something like R4, R3 attached to R1, R2. That checks out. We cannot have R1, R4, R3, R2. That cannot happen. Does that sort of kind of make sense? Yes, good, because that was wildly embarrassing. Okay. So, do we have any questions, comments, concerns, anything of the sort for this reaction? Okay. Doesn't look like it. So, cool. I will zoom out so you can see all of the Wittig stuff at once. So on a scale of 0 to 5, how do we feel about the Wittig? .95. Someone just said yes, which I relate. Me too. 4.5, 4.5. Okay, cool. Cool. So I didn't look like a weirdo for nothing. That's good to know. Okay. So now let's do a couple practice problems. There's this naming section, but I'm going to save this for the exam review because we've done all of this. I'm just was naming everything. So we already did these ones last time. So I want to do some new ones. So I'm going to go to the last page of the handout and we're going to do the Rosemary method and not just the Wittig one. So let's zoom on over. So we have an alcohol plus acid. What reaction is this? Acetal ketol. Cool. We start with a ketone. So it's going to be the ketol reaction. And since we have an acid, are we going to stop at the hemi or are we going to go all the way to the ketol? Ketol, cool. So we're going to take this and attach it 2 times to the carbonyl carbon. So we get so when do you know when to stop? So if you have an acid, you go all the way to the ketol. If you have a base or you have nothing down here, then you stop at the hemi. All right, so for the second one, we have what kind of amine? Is it primary or secondary? And yay, I'm glad you get that part now. Yes, we have a secondary amine. So secondary amine automatically means what kind of reaction? Come on, guys. Enamine, yes. Okay. So it's the enamine reaction. And what is something you need in order to do the enamine reaction? Do 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 do. And alpha hydrogen, exactly. So one thing we have to see is, does this have any alpha hydrogens? Yay or nay? Are there any alpha hydrogens? Yes. Okay, so which side? This side or this side? No, I agree. So what tends to trick people is this. People tend to get tricked because there is oh, that's not what I meant to do. There is a double bond, so there is no hydrogen here, and this hydrogen does not count. So the alpha hydrogen has to be coming off of the alpha carbon, which would be, for example, this carbon or this carbon. So you can never use the hydrogen coming directly off of the carbonyl carbon. So, can we do this reaction? No. So this is no reaction. Bam. Does that idea of the alpha carbon and alpha hydrogen make sense? Because we can definitely spend a little bit more time on it if you would like. One more time? Yeah, absolutely. So let's scroll back up here actually so you can see a drawing of everything. So for the enamine reaction, we talked about this. So we have our carbonyl, and then we have alpha, and then after that would be beta, gamma, delta, etc., etc. So in order to do the enamine reaction, we have to take an alpha hydrogen, which means it has to be a hydrogen coming off of the carbon adjacent to a carbonyl carbon. And beta hydrogens can exist, but we can't use them. So very specifically, it has to be alpha. So, since that's the case, the reaction will not happen if the alpha positions are fully substituted, or if the only hydrogen is available on the carbonyl. Because again, it has to be on the alpha carbon. It cannot be on the carbonyl carbon. Does that make a little bit more sense now? Questions, comments, concerns? Yay! Okay, good. I'm really, really glad. Okay, so let's scroll. Oh, wait. I can wait. Okay, I'm waiting. We're back. And here, alpha, alpha. The last two is no reaction, but the first one can react. So you're talking about between these three? Yes. Okay, so the first one can't react because it has an alpha carbon, but the alpha carbon is fully substituted, so there's no hydrogens here. So if this was a hydrogen instead of a carbon, it would work, but since there are three methyl groups, there are no hydrogens present, therefore it can't happen. So I'll write no reaction because Um, sorry. Alpha carbons are fully subbed. And while you write that down, someone asked how much time are we going to go over? I haven't decided yet. I really wanted to start chapter 17 today, but I don't think that is going to happen. So I think I will go with our original plan. I will schedule an extra SI session for tomorrow where we will go over chapter 17. And then I will record the exam review for you guys. And it will be, someone asked me to scroll down, so just let me know which part you wanted. This is the last thing we did, so I assume it's this. But so, okay. Tomorrow, the last part. Okay. I'm assuming you mean this then. Okay, so yes. SI session tomorrow. Exam review. I will record that and I will post it by Saturday afternoon. And I will send you the cheat sheet on Sunday. And we'll see how that goes and how y'all are feeling. And then if you feel you guys need an extra SI session on Monday, we can definitely do that. Just let me know. Sounds good? Okay, cool. So let's do this one last one and then we can go, or actually let's do two more and then we can call it a day. So we have a secondary amine again. And so we know that's the enamine reaction. And now we do have two alpha carbons, right? And yes, this recording will be up tonight. Okay, so which hydrogen are we going to take? Alpha 1 or alpha 2? Okay, so a lot of students will say alpha 1 because there's more hydrogens present, right? But someone said alpha 2. And I'm actually going to agree with that answer. Excuse me, hiccup. Because if we take alpha 2, then we get a double bond here. And that double bond will be tri-substitute, or fully substituted, I should say. While this one would only be bi-substituted, or di-substituted. So, let me draw out our final product. Bam, 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 bam. The carbon skeleton stays the same. And we know for the enamine reaction, we cut this guy out and we attach this guy. And we know it's single bonded. So we get N like this. And we know that we make a double bond. So what we were talking about is either the double bond ends up here or it ends up here. And as we can see, this double bond is more stable because it is more highly substituted. It has 1, 2, 3, 4 substituents. So that's why we would steal a hydrogen from alpha 2. Does that make a little bit more sense? I know this alpha 1, alpha 2 hydrogen stuff gets to be really confusing at first, but is it starting to make a little bit of sense? Good. Okay, cool. So this last one, NH2, NH2. Which nucleophile is that? Boom, 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 boom. Boom. What do we think? Is this an oxime? No, I was lying. It's not an oxime. Yes, we can do a Wittig example, but someone please remind me if it's two nitrogens attached to each other. Okay, so someone was guessing the oxime / hydroxylamine one, and so I want you to think. That's the one that has the best name. It's like the one that makes the most sense, right? So the hydroxyl implies that there's an oxygen, but there's no oxygen here. Instead, we're going to do the hydrozone reaction, but is this nucleophile the hydrozone? Or is it the hydrazine? Yes. This is the hydrazine. So we're going to form the hydrozone. And the way we do that is we get rid of this and we attach, keep this the same. And we're going to attach the nitrogen and an NH2. And now this guy is the hydrozone. Ta-da! Any questions on how I did this one? Yes, so this one keeps a double bond. So the only one that's going to get rid of the double bond is the enamine reaction. And the, hold on. So out of the set we did today and yesterday, the only one that doesn't keep a double bond is the enamine, but the acetal ketol and the gemdiol also don't keep a double bond. So I misspoke. Okay, so someone said they're confused on what you connect, but can identify what reaction is occurring. So I want you to basically think of this chapter as, depending on what reagent we have, what reaction we have, the idea is going to always be the same. So you're always going to take this and you're going to get rid of it and you're going to replace it with something. So if you know that the hydrozone reaction is happening, which is what you said, all you're going to do is attach the nucleophile, which is this guy, onto the electrophile, which is this guy. And so that's how we get this. And yes, so the ones that are going to keep the double bond, let's actually go through it so you can see it and you're not just like writing in blank space. So the gemdiol reaction lost the double bond at the end. The acetal ketol reaction also lost the double bond at the end. The imine reaction keeps the double bond at the end. And let me zoom out so you can see both mechanisms. So the imine keeps the double bond at the end. The enamine does not keep the double bond at the end. The double bond is on the carbon. So the nucleophile is single bonded, but there is a double bond present. The hydrozone and phenylhydrazone reaction both keep the double bond. The oxime reaction keeps the double bond. And the Wittig reaction keeps the double bond, but it's kind of weird. It's different. You know, it's just kind of different. One thing I do want to mention about the Wittig reaction is this is different from all the reactions because it is not reversible. Because you make a carbon-carbon bond. Bye-bye to the people who have to go. And you're also very welcome. I know someone asked me to do an example for the Wittig, and unfortunately, I do not have one on this handout. So tomorrow, I will find a couple Wittig practice problems, and we can cover them tomorrow. Does that sound like a okay compromise? Okay, cool. So I'm going to send the attendance sheet. Nope, that's not what I meant to send. I'm going to send the attendance sheet one more time. Pretty please fill that out for me if you have not. And then, as always, I will be here for another minute or so if anyone has any questions, but we are going to call it a day. So, bye bye. If I don't see you, have a lovely weekend. Happy studying. I will send you an email because I kind of decided what we're doing for the review, so I will send you an email about that. I don't think I'm going to have a handout for the review since we're not doing it live anyway, but I will send you the cheat sheet. You're very welcome. Bye bye. And yes, this will be posted as soon as I can. Bye bye.